Unit 2 Chemistry, Chapter 15, Part 3, pH. So we've said right at the beginning of this chapter that acids have a low pH and bases have a high pH. What we're actually measuring when we talk about pH is the concentration of hydrogen or hydronium ions in solution. Now it's called pH rather than pH3O+, because when we started looking at it they thought that they were just free hydrogen ions. We now know that they're hydronium ions, but we use the two interchangeably. So yes, I know that it's a little bit wrong, but you can figure that out and just deal with it. We calculate it using the log function on your scientific calculator. We are using log base 10. So it's the one which is written on your calculator just as log. Okay, so we take the concentration, we press the log button, and then normally it'll come up with a negative sign in front of it, and we get rid of that. So it's the negative log of the concentration of hydronium, but don't type negative log into your calculator because you'll get an error. Okay, you just type in log of the hydrogen ion concentration and then manually add or remove a negative sign. That is finding if we are basing it off the concentration of hydrogen ions in moles per litre. We can't use any other concentration calculation here. Has to be moles per litre. Okay, we can also reverse it by reversing the log. So 10 to the power of the negative pH will give you the concentration of the hydrogen ions from the pH. Okay, so if we've got an acidic solution, we're going to have a concentration of hydrogen ions of maybe 0.02 molar. We will work out that if we negative log that, we get negative log of 10 to the negative 2, which is 2. If it's a neutral solution, we will follow this through and we will find that we get a pH of 7. And a basic solution where we might have a very, very small hydrogen ion concentration would have this possibly around about 10 to the negative 13. We would log 10 to the negative 13 and get an answer of negative 13. Negative that, so get rid of that negative sign, and we find we have a pH of 13. Okay, so if we wanted to find the concentration of something with a concentration of 10 to the negative 3, we would negative log that, and we would find that the pH is 3. And I'm hoping you're seeing a pattern here, that if it's just 10 to the power of something, then the pH is going to be the same as whatever that power was. Same here. If we've got a concentration of 10 to the negative 4, or we've got 4 zeros before it, then the pH is going to be 4. Now that only works if it's just 1 at the end here. If this was 0.0002, you couldn't use that cheat, you'd have to calculate it. Okay? If you've got a polyprotic, then we're going to have to look at how many protons can be donated. And for the moment, we're assuming that they are fully donated. Okay? So don't worry too much about the fact that we know, for instance, for sulfuric acid, the first one's donated strongly, but the second one weakly. Okay? We're just going to assume that if we've got a 0.3 molar solution, we've got 2 hydrogen ions in there that could be donated. So the hydrogen concentration, ion concentration, is double that. So 0.3 times 2, which is 0.6. We then log this 0.6, because that's our hydrogen ion concentration. Negative that, and we get a pH of 0.22. Okay? And again, we can do it in reverse. So if we've got the pH of 3.2, we can take that pH, 10 to the negative pH, so 10 to the negative 3.2, and that will tell us the concentration of the hydrogen ion. In this case, it's a monoprotic acid, so the concentration of the hydrogen ion is the same as the concentration of the acid. Now, this works really nicely for an acid. For a base, we quite often don't know the hydrogen ion concentration. We have to find it out from the hydroxide ion concentration. Okay? In a solution at 25 degrees C, we know that the hydrogen times the hydroxide ion concentration is going to be equal to 10 to the negative 14. Okay? Now we can either use that directly, so we can say that if I've got the hydroxide ion concentration and I want to find the hydrogen, then I can do 10 to the negative 14 divided by my hydroxide solution. And then I can take that hydrogen ion concentration and I can log it, and that will give me the pH. And that works absolutely fine. The problem with that is that sometimes here you're working with numbers which are very, very small, or which have got very large negative powers, and that quite often results in people getting their brackets wrong and getting confused. An easier route is to find the pOH. Now P just means you've negative logged it. So pH means I negative logged the hydrogen ion concentration, pOH means I negative logged this instead. Okay? So I can negative log my hydroxide and I can find the pOH. Now to get from the pOH, to get to the pH from the pOH, it's easy. We do 14 minus pOH. No powers, no tiny numbers with lots and lots of zeros in front of them to get you confused. So you can get from there to there, either by doing this and then that, but I would suggest the better route is to negative log the hydroxide and then do 14 minus the pOH. Okay. So for instance, we've got a solution of sodium hydroxide. The pOH will be the negative log of that concentration of it. Okay, that's going to give me a pOH of 2. My pH is going to be 14 minus 2, which is 12. I can get that answer the same way via the other route. I just personally prefer this one because I think you're working with simpler numbers. If I've got a dihydroxy base, so here's one with 2 hydroxide groups, OH minus groups, it's the same idea as when I've got a diprotic acid. Okay? To find the hydroxide ion concentration, I double the concentration of the base. So in this case, 0.02 times 2 gives me 0.04. I can then find the pOH by negative logging that to give me a pOH of 1.4. And then I can subtract that from the pH from 14 to find the pH. So 14 minus 1.4 gives me a pH of 12.6.